Good afternoon. Welcome back. This is the second lecture of Michel mini course, which will be given by me this time, Mikhail Belolipetsky, Misha. So the subject is totally geodesic subspaces of arithmetic hyperbolic manifolds and in general of hyperbolic manifolds. From yesterday, we know how to construct finite volume or closed hyperbolic manifolds in any dimension. So we already know how to construct this is the wrong chalk, yeah. There should be right chalk. Thank you. Okay. Thank you. So we know how to construct hyperbolic. This is the soft chalk and manifolds. In fact, have even two constructions. So one is using arithmetic groups and of the simplest type, number theory, and another that was presented in this course of Giovanni Italiano is using Coxeter groups and by gluing Coxeter polyhedra. That construction works only in bounded dimensions, but it's a very useful construction indeed. So the question which we would like to discuss next is what are the totally geodesic subspaces of these hyperbolic manifolds, totally geodesic subspaces. So on one hand, when you have a given hyperbolic and dimensional manifold, you want to look at its subspaces. The most natural from Riemannian geometry point of view, subspaces will be totally geodesic subspaces, and in particular one-dimensional geodesics, and then if they exist two-dimensional totally geodesic subspaces, and etc. And the question is, okay, if they exist, and how many of them, and how they distribute, and all kind of questions like this. And also, if you have your manifold, you may be interested if it embeds or immerses geodesically in some higher dimensional manifold. So it defines natural relation between these different hyperbolic manifolds and orbitals of different dimensions, and it's some natural field to study. So today I will talk mostly about particular type of totally geodesic subspaces that will be defined and introduced during the talk. Surprisingly, or maybe not so surprisingly, in many cases this construction essentially gives all totally geodesic subspaces of a given dimension, and in other cases it may still give interesting infinite families of such subspaces. So to begin with, let us look at, say, example more related to the second construction. So assume you have some hyperbolic Coxeter group, say, acting on a hyperbolic plane. So for instance, some so-called triangle group. This is a group generated by reflections in the sides of hyperbolic triangle. And as we know from Giovanni's talk, if the angles of the triangle will be of the form pi over n, then this polygon tessellates hyperbolic plane by the action of reflections, and it appears as a fundamental domain of the corresponding lattice, discrete subgroup of finite covolume acting on hyperbolic plane. So, well, we are, and the manifolds, as again we know from previous talks, can be obtained as finite sheet coverings of this type of lattice orbifolds. So there is some surface, in fact, countably many surfaces which appears coverings of this triangle orbifold. Now look at some reflection, say, I don't know, R1. Lifts to the is over surfaces that is, it's normally is not going to be geodesic, so it has some self-intersection. It's going to be a closed geodesic, so it runs around this, and then it connects quite complicated curves. And a priori, from this construction, this geodesic comes up with the involution, with the reflection that was fixing the geodesic side of this triangle. So this reflection still appears in some lattice, say gamma 1, that contains this lattice gamma, such that such that the surface S is a quotient of the hyperbolic plane by gamma. So R1 is contained in gamma 1. It's not contained in gamma because gamma doesn't have any elements of finite order, but it still sits somewhere close to it. In particular, it's this infinite extension of the group gamma in the isometry groups, and it has a property that on the universal cover it fixes this line that projects to the immersed geodesic of our surface. So this is an example, but it generalizes. In particular, it generalizes to higher dimensional reflection groups whenever they exist. You can take a side of this polyhedron and look at reflection in this facet and do the similar construction. Now I want to look at some more details. So three-dimensional hyperbolic let's say arithmetic hyperbolic manifolds. So there is a famous book by Colin McLachlan and Alan Reed called that describes with a lot of care and details arithmetic subgroups of the PSL2C, so arithmetic groups of isometries of the hyperbolic PO31. These are the forms with algebraic number field. condition on that quadratic presented yesterday. So linked to this example, arithmetic lattices of simplest type and the quotient spaces of arithmetic type, they have this property that codimension 1 totally geodesic subspace. In this case, it actually says that geodesic and constructed in somewhat similar way. So I will formalize it a bit more, but to mention one totally geodesic subspace before the simplest type, a reflection that respects this quadratic, and okay, it's if and only if. Using reflections in the group of our form with, say, integer coefficients. Interestingly, this is actually if and only if. So McLachlan and Reed proved that Kleinian orbifold has codimension 1 totally geodesic subspace if and only if it's defined by a quadratic form. So this is a result, and it is explained in the book, but it was proved in one of the papers. So that as long as you have a form, you involutions totally geodesic because of hyperbolic always so these reflexes is a geodesic and symmetries in all. Well, so then there are type 2 sub. I'm not going to define, but I will say something, explain what it means. So to define this type quaternion say D over, again, a totally real number field. K here's O. Then instead of considering okay, K with integers O, and we were looking at quadratic form. Now you look at a skew Hermitian form. So take a form F, she's matrix now is means that I, J are elements of this quaternion algebra, which satisfy relation of the transpose conjugate. Yeah? So Ij is equal to minus Iji star, where star is the standard involution on the quaternion algebra, which maps, I to minus I, j to minus j, k to minus k. Let's the base field k fixed. So, well, there are these skew-Hermitian forms. You probably saw them in the courses of algebra. And now this form is admissible if it has, if over, now take D tensor R power m, this vector space, it has, this will, here it will be a quadratic form, and it has to have signature, okay, 2m minus 1, 1. Moreover, its Galois conjugates defined as in the previous talk, exactly you apply Galois automorphisms of k to the coefficients, to everything. F sigma have signature 2m0, so totally definite. Well, it's the same type of condition which tells you that in one place, so in the fixed place, the identity of the field, this unitary group will be isomorphic to the group of, so it will be non-compact, and it will be isomorphic to the group of automorphisms of the hyperbolic space of dimension 2m minus 1, and in other places it's compact. Then you can take, again, now you take an order in the quaternion algebra, or this will be just order. Okay, this will be integers, and this will be order in D. The group of the matrices, unitary matrices with coefficients in this order, will be an arithmetic subgroup of, well, actually of O n1, let's say, where n is, what is n? Okay, n is 2m minus 1. So this is the sketch of the construction of the arithmetic lattices of type 2. What it tells you is that it's similar to type 1, but instead of quadratic forms, you use Hermitian, or, well, okay, by some convenience, skew-Hermitian forms. And because, okay, there is this standard involution here, it imposes the parity condition on the dimension, and these type 2 groups can be constructed only for, well, when this space has even dimension, so only for hyperbolic spaces of odd dimension. In particular, in dimension 3, we have type 1 and type 2. In dimension 2, we only have type 1. So it's modulo over the integers. It's like a generalization of the integer ring, but when you talk not about the field, but about the division algebra. I don't want to go really into these number theory details because I want to talk more about geometry. This is one of the parts which you can find quite detailed in the book of Colin and Alan, although they do it slightly differently, and I am coming to that part. Well, to get there, let me mention that there are also type 3 lattices in PO 3.1. So what is type 3? It's those arithmetic subgroups which are not type 2 and not type 1. So as you can see by the construction, type 2 and type 1 exist for so type 1 exists in all dimensions, type 2 exists in all odd dimensions. Type 3 is something which appears due to exceptional isomorphisms between algebraic groups of certain types. So these exceptional isomorphisms, as Leonet explained in his lecture, appear in hyperbolic in dimension 7 because the Dynkin diagram there has particular symmetries, but they also appear in hyperbolic dimension 3, where, okay, the Dynkin diagram is just a point, but there is still an extra symmetry. Well, so this type is particularly interesting. Now, after saying all this, I can tell you that there is an somewhat easier way to construct all arithmetic lattices in PO31. So that is because due to, again, exceptional isomorphism between, say, so if you look at this group and take its connected component, and it will be orientation preserving isometries of the hyperbolic 3 space, and this is isomorphic to PSL or PGL, let's say PSL 2C. And that is another group that is, okay, both are groups of orientation preserving isomorphisms of hyperbolic 3 space. Now, in this group, you can, again, use quaternion algebra over a field, but this time over a field with one complex place, and construct all arithmetic lattices in PSL2C using units of the orders of quaternion algebras of the fields of one complex place. So I will tell it really quickly. Can construct all arithmetic lattices as using this quaternion algebra over fields with one complex place, exactly one. This construction gives you all at once. This is the construction that is explained in most details in the book. Okay. The book. So if you are interested, please take the book. It has one chapter about quaternion algebras. In fact, it has two chapters about quaternion algebras, one chapter about orders in quaternion algebras over number fields, and it gives you very detailed explanation of this construction. So I want to get back to the question about geodesic subspaces. We know that this is one of the reasons when it's useful to actually look at these arithmetic lattices in PSL2C as type 1, type 2, type 3, because, okay, here they appear all at once, but then you see that actually they're different. You know, some of them have totally geodesic surfaces and some of them don't, and who knows why? Yes?
When do type 3 lattices exist?
This could?
When do type 3 lattices exist?
So why or when? When? They exist only in dimension 3 and 7. and they do exist both in dimension 3 and in dimension 7. So we had a talk about utilitarian lattices last week. We didn't speak much about exceptional lattices, these type 3 lattices in dimension 3. They're somewhat hidden a little bit, in part because of this definition. But there are some intriguing open problems about type 3 arithmetic lattices in dimension 3. So maybe we will get to that later during this course. Now, so what about totally geodesic surfaces? Now I want to go back in time. So I want to talk about Jorgensen evolutions. Jorgensen's involutions. Well, let M be a hyperbolic, arithmetic hyperbolic 3 manifold. This soft shock goes quickly. And assume that we have a pair of, so actually we do have a pair. Let's choose a pair of non-commuting loxodromic elements in gamma. So I want to choose them a pair of loxodromic elements such that they generate not non-elementary subgroup. These pair, such elements always exist because, okay, gamma is non-elementary. Let's assume that gamma is co-compact for simplicity. Then we don't have parabolics. Actually, then if gamma is co-compact, then all non-trivial elements, co-compact or free means all non-trivial elements are loxodromic, and we just take 2 of them, which such that one is not a power of the others. Okay, so loxodromic and generate non-elementary subgroup. In hyperbolic 3 space means that we choose 2 non-intersecting geodesics, which are the axes of these loxodromic elements. So how to denote them? Axis of, okay, A and B. These are axes on A and B. Now, Jorgensen in 78 published a 2-page paper in which he observed that, okay, Jorgensen observes the following. From 78. Consider matrices of these loxodromic elements as matrices in SL2C. So, well, strictly speaking, these are matrices in PSL2C, but so they're defined up to sign, but you choose any sign will work. Choose corresponding matrices in SL2C. Then what Jorgensen noticed is that if you look at the Lie product of these matrices in GL2C, so what is Lie product is AB minus BA in the group of 2 by 2 matrices, not necessarily. Now you don't have, well, okay. Not in the group, in the ring of matrices, right? Then this Lie product has trace 0. So it's a first exercise for you to check. In fact, it's invertible. So it's, in fact, element of GL2C. So this is exercise 1. Then what you do is you divide by determinant, project and get an element in SL2C, which we will denote by tau AB, and this is an involution because the trace is 0. An involution. In fact, so then he observed, so what is exactly this involution? It has clear geometric meaning. You take two, we have two geodesics in hyperbolic 3 space, and you take common perpendicular of these two lines. It exists and unique. Shortest, common perpendicular. It exists and unique by elementary hyperbolic geometry, and tau AB is nothing else as a half turn, so order P rotation around this geodesic. So it maps A to A inverse, B to B inverse, and this is how it acts.
So you're assuming the axes don't meet?
We want this loxodromic axis not to meet. This is enough or not? No. So what? If they are perpendicular, they will gamma is torsion free. Can they meet? Okay, this is another exercise. Do we need extra condition here that they don't meet? I require that they don't meet, but I think that it might already follow from assumption that gamma is torsion free, and this, but check. We will discuss tomorrow. Tomorrow we will have exercise session. Well, this is Jorgensen evolution, and it's a really beautiful observation that trace is 0, and you get nice geometric construction of an element in. So this, now what is this tau AB? Let me remove the bar. This tau AB, it's not an element of gamma because gamma is torsion free, but it's somewhere not too far from gamma. Because it is how it is, right? And here comes the second exercise, which was actually a proposition of Lackenbill, Long, and Reed. So, exercise 2. check that this element tor AB, when gamma is arithmetic, here we need assumption that gamma is arithmetic. So when gamma is arithmetic, this tor AB is an element of commutator of gamma. Commutator, I think, did not appear yet this week, but we are going to talk more about it. Now let me just define this group. So it's all elements in our Lie group that have a property that conjugation by G of gamma intersection with gamma has finite index in gamma and gamma G. So it's some group which obviously contains gamma, but it's bigger. It's a group. It's easy to check. The commutator is a group, and this group is important in study of arithmetic groups and in general of study discrete groups. We will come to it later. By now, the exercise is just to check that tau AB is an element of commutator. I know. So this requires some work. It's not obvious. It was first observed by and proved by, well, I think it was proved by Reed and Long, but it appeared in paper by Lackenby, Long and Reed from 2008. So how many? 88, 90, 30 years after after Jorgensen. And I don't think people knew this before this paper. This fact is crucial in the following work. So we should have a break sometime soon. I will say why it's crucial, and then we make a break. So there was this paper, and then the following paper by Mark Lackenby, in which he proved he proved surface subgroup conjecture for arithmetic Kleinian groups. And he proved it before Markovich and Kahn. And he proved it by a different method. So the idea of Lackenby how to prove that conjecture was that in arithmetic case you have this element, this involution, nice involution in commutator, and they did a bit more. These people did a bit more. They found another involution in commutator which commutes with this one. So they were able to find two commuting involutions in commutator of any arithmetic Kleinian group. What does it mean geometrically? It means that there exists some arithmetic three-orbifold commensurable with this manifold that has a singular vertex in its singular set of particular shape. And that vertex was enough for Lackenby to do some flow and very beautiful kind of min-max argument to find the surface subgroup. It's totally different proof from Markovich and Kahn, but it only applies to arithmetic groups, and it uses dramatically the Jorgensen involution and this fact that it sits in commensurate. So it's a good, the fact is an exercise. I know two proofs of this exercise. One proof, well, maybe I can find a third proof, but okay. One proof was familiar to us. Then in our work with Kolya Bogachev, Leonid Slavich, and Sasha Kolpakov, we gave another proof. And okay, our arguments sometimes somehow more general, not so attached to hyperbolic 3 space. Well, let's make a 5 minutes break, because otherwise too tough, and then I will continue more. Yeah.
Why was Jorgensen interested in this conclusion?
He was interested in geodesics I think on hyperbolic free manifolds or on Riemann surfaces. Well, he was doing complex analysis, right? But so the paper is called Geodesics on Hyperbolic Manifolds, I guess. I have a I don't have Jorgensen's paper here, but I have Lakenby, Long and Reed. It's called Closed Geodesics on Riemannian Surfaces. So he was not even talking about hyperbolic three manifolds, but the same argument applies also for surfaces. Okay. Obviously, the axis of this involution is a geodesic. And when you find involution, it gives you way to construct geodesics, and it gives you also a way to control geodesics. So that's probably what was his interest. Other questions? Thanks. So before I restart, let me say that today, unfortunately, we are not going to have a third mini course because Giovanni is not well, but we really hope that he will be perfect tomorrow, and his course will continue tomorrow. Because of that, maybe I will allow myself to talk a bit more, because I want to to give one example at the end. And to get to that example, I need to say some more things. Well, I hope that you all liked Jorgensen involutions and you like them even more. In the paper which I mentioned already, so there is a paper with Kolya Bogachev, Slava Kolpakov, and Leonid Slavich. So Kolya and Leonid were here last week. What we did, well, one of the first results of this joint project was to generalize Jorgensen involution to other type 2 groups. You see, in type 1, we know how to construct total geodesic surfaces in all dimensions. In type 2, so the question is, what about type 2? Already, for all arithmetic subgroups, Jorgensen involution gives us natural construction of geodesics. Well, we know from Riemannian geometry also that there are closed geodesics on closed, say, hyperbolic three manifolds, but this gives us some other construction of geodesics that is interesting by some reasons which will appear later. Now, in dimensions higher than 3, when you look at type 2 lattices, okay, there are no surfaces there, codimension 1 subspaces, and okay, there are geodesics, but other like codimension 2 subspaces or not. That was the first question of interest, and it appears that it turns out that generalized Jorgensen involutions exist in commingerator of gamma for gamma okay, pure odd dimensional arithmetic lattice of type 2 in fact, of type 1 and type 2. And their fixed points are going to be codimension 2 totally geodesic subspaces. Point set projects to codimension 2 to geodesic subspace. Subspaces. So this is quite a bit better now. Say take any odd dimension which is not 3 or 7. Well, say not. In fact, for 3 we also have not equal to 7. Then, if it's type 1, then we have totally geodesic surface. In fact, at least some finitely many of them we can easily construct. Hypersurface, I mean. And if it's type 2, we have codimension 2 totally geodesic subspace, at least one, and again. In fact, it will be explained a bit later, maybe tomorrow, that or on Thursday, that when we have one, we always get infinitely many, countably many, in arithmetic case. Well, so it's quite nice. It's generalization of Jorgensen involution. Starting from here, maybe I erase this too. Well, from this result, there are two ways to continue. One way is to try to understand the last remaining open case, which is trilitarian 7-dimensional arithmetic hyperbolic manifolds, and that took us a lot of effort, and Leonie gave talk last week about it, which is on YouTube. Because it corresponds to D4 Dynkin diagram, which has group of automorphisms over the 6. Okay, that is really Leonie did as best as he could in his 1-hour talk, and I think it's better if we refer to that. Now the other natural question is, so it looks like there is some general pattern. There is like reflection or rotation, and it's fixed point set, and reflection is not in the group, but somewhere not too far from the group, and this fixed point set projects into totally geodesic subspace. So while looking at various examples of this type, we make the following definition: an immersed totally geodesic let's say suborbifold.
So, sorry, can you say how, more or less, how you build this involution in this theory? Like you say, you generalize it, right? I mean, like in what you showed, you use like 2 loxodromic elements and do some things. Like
Look,
what's the input for the involution?
Look, my plan is to give a couple of other general statements and then give one example. Well, I was not planning to give. Okay, maybe next time I give one example. The construction requires a bit more technical data that I gave here. So you really need to. We have construction in the paper, so but to make it explicit, one has to work with more care all the ingredient of the definition. And Well, I think you need to be careful, and also you want to understand. Okay, you can do this, but then what is the fixed point set?
If you go generalize evolution this type.
Well, the idea is simple. Yeah, so you just take and generalize it in. You see, you want codimension 2 subspace. So in this higher dimension, there are already not only rotations, but like rotation, various types of elliptic elements to begin with. We look at agent spaces and to see the dimension of the fixed point set. And well, there is Hermitian form. So it's not something terribly difficult, but I will not be able to do in 5 minutes, sorry. I want to define these FC subspaces. Immersed totally geodesic suborbifold N in a arithmetic orbifold M. Is called an FC subspace. FC means finite centralizer. Okay, why it's finite, it will be clear right now. It's centralizer, so clear. If there is a finite subgroup F in commutator of gamma, whose fixed point set projects into N, onto N. And so what does mean projects to N? And this N is nothing else as a quotient of H by stabilizer of H in gamma. Yep. So the examples of FC subspaces are, well, these spaces obtained as fixed point set of Jorgensen involutions in their generalized form, or any so perhaps example proposition. Codimension 1 totally geodesic subspace of an arithmetic. M is always an FC subspace.
If you implement diplomatic involution on the Riemannian surface, fixed point set will be an example of this.
Yeah, else. So there are many examples. Somehow, the only interesting examples of finite groups which we found in this context are groups of order 2. So not necessarily reflection, but okay, can be rotations, can be like rotations in subspace of some whatever dimension k, but okay, it makes most sense to define it this way in general because it's possible, and of course it can be that commutator of gamma, say, contains elements of order 3, but in that case we can also find elements of order 2 which have the same fixed point set, maybe, or maybe not. And also they can be not cyclic finite subgroups. However, so far all our interesting examples come from involutions of different type. So before getting to promised example, let me state one more result. This I really wanted to show because we have enough information for do this. So again, M is arithmetic and defined over field K. So defined over field K means it has clear meaning in the previous talk of Matthew when you have a quadratic forms with coefficients in K, so in number field, totally real number field. And that is your field of definition. That's the field whose Goa conjugates you apply in order to get this compact form of field of definition. In the case of Hermitian, skew Hermitian forms, there is also this totally real field K, and this is your field of definition. And now N is totally geodesic. In M, so the theorem says that and I want N to be of dimension bigger or equal than 2. This N. Then N is also arithmetic. And it's defined over field K, big, okay, now it's not good. Defined over field L, which contains K. And in particular, okay, this applies to FC subspaces. So FC subspaces are by definition total geodesic subspace. It already comes with some finite order element attached to it, and it's going to be defined over field L as here. The interesting part is that this inclusion can be strict. So, well, definition which we suggest that if these fields are equal, then N is called subform space. And it is automatically FC subspace. So definition proposition, yeah. Subform space is always FC subspace. In general, what can happen is that, so the general picture is as follows. We have N totally geodesic suborbifold of some arithmetic manifold M. Then there exists some intermediate totally geodesic subspace that contains n and contained in M. So this inclusion is, and it's uniquely defined. Okay, this can be equal also. So this inclusion is a subform space. And this inclusion is a Weil restriction of scalars. So what is Weil restriction? Roughly speaking, if you say look at, I don't know, quadratic field Q root 2, you could look at it as two-dimensional two-dimensional vector space over Q by taking example, say of not even example, but like some intuition for Weil restriction is consider field Q root 2 as a, and so these are what? These are elements of the form A plus B root 2, where A, B rational number. So you can think of it as also as these pairs of A and B rational numbers. So this way it appears as a Q square. And this, so any finite extension of Q can be thought of as a Q to the power D. And this way, say, a group of matrices over, or quadratic, orthogonal group of quadratic form with coefficients in, say, this field can be thought of as a subgroup of the twice times bigger matrix groups with coefficients in Q. And this is restriction of scalars. But now we want to apply the restriction of scalars to admissible groups. So there is some care which is needed to see that, for instance, you don't lose this admissibility condition, and everything works, but apparently it does. So to conclude, I wanted to show one pretty explicit example of this FC subspace, of this inclusion, of this strict inclusion. When you get a group defined over quadratic extension of Q as a subgroup of a arithmetic group defined over Q. So this is plan, and I have notes here, so I quickly go through this example. Any questions?
Can I explain again the Weil restriction? So you're identifying the field with the Q square, but what is exactly the restriction?
Well, it's a functor. I can explain you later. Maybe let me go through example, because I think if I start from scratch.
Do you need arithmeticity in the definition of FC subspace for some reason, or is it just
Actually, yeah, thank you, Stefan. It's a good. We don't need it in definition. We have the same definition for subspaces of non-arithmetic cases. What happens is that in non-arithmetic cases, you may know the commutator is much smaller. It's also lattice, so there is not so much space to choose these finite groups. It can be that in non-arithmetic case, it may happen that commutator doesn't have any finite subgroups, even for say, hyperbolic 3 manifolds, non-arithmetic. And then, okay, definition is not so useful. But for arithmetic, say, for non-arithmetic Coxeter groups, it's pretty useful because you do have finite subgroups there corresponding to reflections.
Is there an example of a totally geodesic subspace of an arithmetic manifold that's not FC?
We do have examples. We know a bit more than I explained here. So we know that up to certain codimension, which is roughly the half of the dimension of manifold, all the total geodesic subspaces of arithmetic manifold will be FC. And below that codimension, so what you do is you apply this value restriction construction, and then it's possible to get non-FC subspaces. And we tried to kind of modify definition of FC subspace, but we could not find a definition which would include that. Maybe it's possible, but we were not able. So, and after some codimension, we do have examples that are terribly non-FC. Okay.
High dimension or low dimension?
For high codimension.
Geodesics.
Hmm? Okay, in hyperbolic 3, in arithmetic 3 manifolds, all total geodesic subspaces are FC, and all geodesics are FC.
You have geodesics which are not FC, in a bigger dimension.
Well, in non-arithmetic, you can have easily. In arithmetic, okay, in dimension 3 you don't have, because of these Jorgensen involutions. You play a little bit more with these involutions, and you can, given any hyperbolic isometry in the group, you can construct element involution in commutator whose axis is exactly this element in hyperbolic 3 space. So that kind of covers them all.
For bigger dimension?
For dimension 3.
Yeah, for bigger.
Bigger? Yeah, that's a good question. So,
I thought you can just decompose your space geodesics into rotation that alone.
about geodesics, so certainly our counterexamples, kind of our examples of non-FC subspaces, will not answer your question. So I don't know the answer now. Maybe it's always true that geodesics are FC in arithmetic manifolds. Okay, I need to think about it. Good question. Thank you, Misha. Okay.
For dimension 3, it's okay because the rotations is an Euclidean group. But in higher dimensions, in our regular element, you're going to have this non-Euclidean rotation. It would be very hard to agree with that. I think what's special about dimension 3 is that the rotation group normal to the geodesic is Euclidean.
Well, he's talking about one-dimensional geodesics, right?
Yeah, that's what I'm saying. So in higher dimensions, you have a bigger normal bundle. And so an R regular element is going to be an element of a non-abelian. It's going to be, the whole is going to be a non-abelian orthogonal. So the central, you'll have nothing centralized.
Well, you just want to put this R regular element in commutator. And there are a lot of R regular elements. There is, in fact, there.
Like you'll have things that are.
Hmm?
My point is there will be geodesics.
They what?
There will be geodesics that cannot be FC.
They can be geodesics which are not axes of regular elements.
We can talk.
Okay, well, maybe you're right. Well, so the example I want to show is of a field Q. I want to model n-dimensional hyperbolic space, so I have n+1 dimensional vector space over Q with a standard basis, say, okay, standard basis is 0, U. So the desire is to make things explicit in order to, those who don't believe them can check. Now I look at the quadratic form, of block diagonal of the shape. Okay. In fact, with this matrix, so I just single out one block, and then there are some blocks of 2s, which are how many of them? Well, m blocks of the form. So in particular, can take m equals 1, then it's three-dimensional hyperbolic space, right? So it's going to be m equals 1, going to be Q4, and yeah, three-dimensional space. And now consider, I want to take some special chosen matrix in an orthogonal group of this space. And this transformation has a bunch of interesting properties which are easy to check. Okay. Here is the first block, and then okay, there are some numbers here. Basically, root 5 enters in the picture. And again, m copies of this block. Okay, all others are 0. So another exercise is the following. There are some properties of m which are easy to check. So m is invertible. Well, that you can do. The other interesting property is that if you act by m by conjugation with this matrix m, the result will be, so apply m to some matrix n in GLN plus 1. And then I claim that this new matrix will have entries who are rational polynomials in coefficients of n. So rational. And so the entries of this, let me write down, are rational polynomial functions with coefficients in n. Well, this a priori doesn't have to be the case because there are roots 5 here, but when you apply m and its conjugate to n, what happens is that root 5's roots disappear and rational functions appear. This happens from time to time in algebraic geometry, and one example is here, right? You can check if you don't want to suffer too much, take m equals 1. But the same applies to every m.
So the entries are rational? So the entries of n are rational? Or
No, the entries of n are whatever. So denote entries of n will be variables, and what comes here is rational functions of the rational polynomials functions in these variables. Moreover, there are some other properties. Okay, this may be easier. Matthew told to write this way. Yeah? M transposed AM is equal to A. So M preserves this matrix, and M is a matrix of involution. Also easy. So the corollaries of these three properties is that M is a matrix of involution in the group of rational, because here are the rational functions, so it's rational automorphisms of this quadratic form. F where F is a quadratic form with matrix A. In other words, so if we denote by gamma the group of integer automorphisms of this quadratic form, so this arithmetic group, by the first definition, the simplest possible case over Q, arithmetic group in isometries of the n-dimensional hyperbolic space, then M is an involution in commensurator of gamma. Okay, so M defines an FC subspace of the quotient orbifold corresponding to gamma. Of what? Of IHN mod gamma. But we suffered a bit writing down the coefficients of the matrix and checking that some products are of these quadratic irrationals are in fact rational numbers. So we can say more about this FC subspace. We can say exactly what it is. Let's determine this FC subspace. So this matrix, when it acts on the vector space Qn plus 1, it's okay. It has eigenvectors and eigenvalues and eigenspaces. In fact, its eigenvalues, because it's involution, are going to be 1 or minus 1. So let's consider eigenspaces. This is how we understand what is the fixed point set. Yeah, we can consider fixed point space and its orthogonal complement. So eigenspaces of M, say V plus corresponding to eigenvalue 1. And okay, a little computation shows that it has a basis of the following form: E0 we did some computation on computer, okay, but I will write the result: E0 minus root 5 E1, and then E2I plus root 5 minus 2 E2I plus 1, where I is 1 to m. Okay, this is a basis of positive vector space, and the negative corresponding to eigenvalue minus 1 of m is given by, okay, coincidentally it's just Galois conjugate of this basis. So well, this way explicitly we know the eigenspaces of M. And now the final step. We want to compute restriction of the quadratic form F that we started from to these eigenspaces. Because we want to, so what is our goal? Yeah? Our goal is to write, so we have a C subspace. We know that it's arithmetic, but what is its quadratic form? So we know that it's arithmetic. We know already from, say, general theorem that it's of first type. So it should have field of definition and quadratic form. So we want to write down this quadratic form and this field of definition. For that, we looked at we determined the action of M on the vector space, and now we are going to write the quadratic form. And okay, we wrote it here. I will try to copy. So there are two parts. A restriction G will be a restriction of F to V plus, and it's a quadratic form given by a diagonal matrix with so it's -2 root 5 so what is the dimension? I'll just write matrix. Has matrix have the same problem with arithmetic. I have to divide n plus 1 over 2 and then I think take -1, but okay, that's already complicated. But if I write down the matrix, it's easier a little bit because the matrix has one entry -2 root 5, and then all the other entries are 20 minus 8 root 5. And okay, there is appropriate number of them. Also, this way, I don't need to introduce new variables. Very nice. So this quadratic form, notice that these numbers are positive, okay? 20 minus 8 root 5 is positive number. If you don't believe me, let's go ahead and check. And its Galois conjugate, of course, is also positive because that is easier, right? Now, we still need one more matrix. Okay, let me move here. We need also to write down this Weyl restriction. We need also know what is a restriction of f to v minus has matrix that can be also written down. So this matrix is, of course, with respect to this basis, right? To write down the matrix, I need to fix the basis. I chose the basis this way, of this subspace, and this is the matrix. And again, the matrix with respect to basis B minus is going to be, again, diagonal with one entry 2 root 5, and the other entries are, okay, Galois conjugates of this. So this is positive definite quadratic form. All numbers are positive, and this quadratic form is signature 1n, and also H is Galois conjugate of G. So more precisely, G has signature so n minus 1 over 2, 1. And H is G sigma is totally positive. And now, well, now the conclusion is this, that this orbifold N, the FC subspace, the FC subspace of N, of M, is defined over Q root 5 because it has this exactly this quadratic form defined over Q root 5, and it sits inside N exactly as shown by this construction. So the first block of half dimension fits by this matrix, and then the second half is Galois conjugate, which is given by this matrix. And okay, this is totally positive, so indeed the subspace is an arithmetic subgroup of our original group, and our group was defined over Q with this diagonal quadratic form. Our subspace is defined over Q root 5 and has this quadratic form. So all can be made very explicit in this construction. Some more details can be found in the paper. And perhaps this is a good time for me to stop. Thank you.